in the section hours and other information concerning the TA. So if you, to be sure you have the up-to-date information, you should check the website. I think it changed on Friday. Last time, we talked about our fundamental assumption for a closed system and its consequences. The assumption can be stated as all accessible states of a closed system are equally likely. And we define two important concepts, which we'll be talking about from now on. The one was the entropy. If we consider a system where we specified macroscopic quantities, like, say, number of particles and energy to some reasonably high precision, the entropy means the natural log of the multiplicity, the number of states. So each of those states has a probability 1 over g. Under our assumption, it's a uniform distribution. The log of the number we call entropy. And we also define temperature. We can say that 1 over the temperature tau is partial derivative of entropy with respect to energy with the number of particles fixed. And we saw that this definition of entropy corresponds to this definition of temperature corresponds to our intuitive notions about temperature, namely that if I have two systems which are isolated from one another, but then I bring them into thermal contact so they can exchange energy, now, the joint system seeks out its most probable configuration. In fact, nothing happens macroscopically if the systems have the same temperature. They're already in the most probable configuration. We call that equilibrium. If one is hotter than the other, say system 2 is cooler than system 1, then to establish equilibrium, to seek out a more probable configuration, heat will flow from the warmer system to the cooler system until equilibrium is reached. We also talked about the issue. Yeah, question.
Hey, question. So at the most probable configuration, does d sigma du equal 0?
No. D sigma du is, so you're saying, so here's why you're asking the question. You're saying we want to attain a maximum of the entropy, but if we actually have a closed system, the energy of a closed system is actually fixed, right? So there isn't a way for the energy of a closed system to adjust to seek out a more probable configuration. Instead, we consider bringing two systems, initially isolated from one another, into contact. And then what you're saying is essentially correct. If we, I could have answered yes. Now we have a constraint. The sum of the energies of system 1 and system 2 is equal to some fixed quantity. And so I can ask, if I want to maximize the total entropy of 1 and 2 as a function of the energy of 1, then derivative of sigma total with respect to energy of system 1 is 0. Okay?
So in a closed system, what what does temperature mean?
Well, first of all, in a closed system, it tells us something about what will happen when we bring two systems, which are initially closed, into contact, so that the system becomes open, right? And that's non-trivial information, right? You have two closed systems, and all you know is something about how the entropy varies as a function of energy. That allows you to predict what's going to happen when the two systems come into contact. And we'll see other implications of entropy and energy and temperature for closed systems as we go. Okay. And we also talked about deviations from equilibrium, fluctuations about equilibrium. And we said that if the system is really large, there are always fluctuations from the most probable configuration, but they're typically small. Very large deviations from equilibrium, although they can occur in principle, are very rare. The system's really large, even a relatively modest deviation from equilibrium is extremely rare, suppressed by the exponential of a very large number. Then we talked about open systems. We talked about open systems because every system really is an open system. You can't perfectly isolate any system from its surroundings. So if we want to model systems accurately, we should consider a system in some sort of contact with a much larger system, which we call the reservoir, and you can think of it as the rest of the universe. And suppose in particular that there's thermal contact between system and reservoir, so energy can flow back and forth between system and reservoir. Now, we no longer necessarily will require the system to be big. The reservoir is big. It's everything but the system. So we're imagining a system in contact with a much larger system. Okay? So now we'd like to understand, if we look just at the system in contact with the reservoir, what kind of probability distribution we should expect to see for the states of the system. Well, in particular, suppose I single out two microscopic states of the system with energies E1 and E2. Okay? Maybe it's just a two-level system. Maybe that's all it's got, or two levels. Small. And now I would like to know the relative probabilities of the system occupying state 1 or state 2. Okay? Well, the ratio of probabilities, well, we use our fundamental assumption, but we apply it to the reservoir. When I say system 1 or system 2, that's a state of the system with no degeneracy. It's a unique state. Okay? So what's the difference between them as far as our fundamental assumption is concerned? It's how many states the reservoir has. If the energy of the system changes, if it makes a transition from E1 to E2, its energy changes. Where does it come from? The overall system is closed. Should have said that. Its energy is fixed. Okay? So if the energy of the system increases, that energy came from the reservoir. If that energy increases even more, the system borrowed even more energy from the reservoir. When the energy of the reservoir changes, the number of its accessible states changes. And that will change the relative probability of the two states of the system. We can say that this is the multiplicity of the reservoir when it has the total energy, call it U naught, minus the energy that the system borrowed, divided by the multiplicity of the reservoir when the system borrowed energy E2. Right? So then we said, okay, suppose we take the log and we do a power series expansion. Why could we do that? Because we're considering the reservoir to be very large, and that allowed us to say that if I take the second derivative of the entropy of the reservoir with respect to the energy of the reservoir, that in the limit of a very large reservoir, we expect that to be very small. So if the volume of the reservoir is large, that second derivative is actually suppressed by a power of 1 over the volume. And you can think of that as just being like dimensional analysis, sort of. We argued that entropy is really an additive or extensive quantity. System gets larger, entropy scales up like the volume. Same thing for energy. When we differentiate once with respect to energy, we get an intensive quantity independent of system size. That's what we call 1 over the temperature, right? If we differentiate again, we get a quantity which scales like 1 over volume of reservoir, which is huge. It's essentially 0. So we don't have to go any further than first order in our power series expansion. All the other terms become extremely small and can be neglected when the reservoir is really big. Okay? And we concluded, on the basis of that argument, since all we had to keep was the first derivative, the zeroth derivative is divided out between the zeroth derivative of the logarithm and the multiplicity divided out between numerator and denominator. And so what we were left with was that the probability of the system being in some microscopic state with energy Es was proportional to e to the minus the energy of the system divided by the temperature. The temperature of what? The temperature of the reservoir, right? It came from differentiating the log of the multiplicity of the reservoir with respect to the reservoir's energy. Now, this is the temperature of reservoir. And this is the energy of system state. So, it's a little bit confusing because we're talking about two different ensembles of states of the system. When the system is closed, according to our fundamental assumption, we can consider a probability distribution which is uniform over accessible states. All states equally likely. Okay? When the system is open, we're saying something different. I kind of cluttered this up, didn't I? Making it harder to draw a box around it. But we're saying that at a fixed temperature of the reservoir, more energetic states of the system are less likely. Okay? But it's following from the same fundamental idea that accessible states are equally likely. In this case, though, we're applying it to the reservoir. And we're considering two states of the system which are completely specified with no degeneracy. Okay? Makes sense? It tells us then that if the temperature of the reservoir, well, what does it tell us? I mean, qualitatively, we have these two states. Let's say there's some energy splitting, call it delta E, between them. And then there's another quantity with the dimensions of energy. That's the temperature of the reservoir. When the temperature is small compared to the energy splitting, well, what happens? The system is much more likely to be in the lower energy state, right? The relative probability of being in the higher energy state is suppressed by this very small exponential factor. If the temperature is really large compared to the energy splitting, what happens? The two states are almost equally likely. Okay? So the temperature somehow controls the energy scale of the fluctuations of the energy of the system when it's in contact with the reservoir. Okay? So this equation, the sloppy equation I put a box around, is called the Boltzmann distribution. That's where we left off last time. Any questions about that? Okay. Well, we have a probability proportional to something. Of course, it's convenient to normalize that distribution. Normalize means make all the probabilities sum up to 1. So we define something which is denoted z, and it's a function of the temperature. What is it? It's the sum over all the states of the system, e to the minus energy of the state divided by temperature of the reservoir. And that quantity, for obscure historical reasons, is called the partition function. Never mind why. A better name for it might be the Boltzmann sum, because that's what it is. It's the sum of Boltzmann factors. This is also called a Boltzmann factor. So the probability for the system of being in a state with energy ES is the Boltzmann factor divided by the partition function. With that normalization, probabilities sum up to 1 like they should. The sum over states of the system, probability of being in that state is 1. Now, we can, so far, system isn't necessarily large, might be, but this applies even if the system is small, maybe a single atom or a single two-level system. We can ask about, on average, properties of the system using this distribution, average over this ensemble, to compute average properties. Just like we did for the uniform ensemble in the closed system case. The energy I'll use U to denote the average energy of the system. Okay? Average over this ensemble, that means I sum over states weighted by energy of the state and the probability of that state. That's what I mean by the expectation value in this ensemble. So writing out explicitly what it is, I sum over states, energy of state, Boltzmann factor of state, divided by partition function. Well, there's a convenient trick for evaluating that quantity or writing an expression for it, which is useful in applications. We notice that if we differentiate with respect to temperature the partition function, well, we differentiate it term by term. When I differentiate the exponential, there's a 1 over tau in the exponential. So when I differentiate by the chain rule, term by term, I'll get energy of system divided by tau squared. There are two minus signs, right? A minus sign coming from the exponential, a minus sign coming from differentiating 1 over tau, giving minus 1 over tau squared. And weighted by the Boltzmann factor. Well, that's convenient to notice because the quantity in the numerator here is the same summation over states, aside from this factor of tau squared. So I can write the average energy, U, as tau squared And then remember, there is a 1 over z here. So I'll put that in front, 1 over partition function, and then derivative of partition function with respect to temperature. Of course, that's just the differentiation of the log of the partition function. So equivalently, I can write tau squared, derivative with respect to temperature, natural log of z of tau is the average energy. I wrote T instead of tau because I'm sloppy. So that'll be handy to know because sometimes we can compute the partition function just by doing the sum and then immediately figure out what the average energy is by taking its log. Well, not quite immediately, but in a few short steps we can take its log and differentiate it, and we know the average energy. Okay. So continuing on this tour of concepts you're very familiar with and how they arise in the context we've been discussing, let's talk about pressure. Well, you know what pressure is. If I had a gas in a box, we can imagine that there's a movable piston which I can use to change the volume of the gas. This is the region occupied by the gas, which has volume V. I could push the system in, push the piston in to decrease the volume or pull it out to increase the volume. And when I do so, work is done, either by me on the gas when I compress it, by the gas on me if I carefully pull the piston out. The work done is the force, if I'm compressing, which I apply holding the handle on the piston and pushing it in, times the amount by which I push the piston forward, call it delta x. We can write the force as force per area, cross-sectional area of the piston, times area, and that force per area is called pressure. So I can write this as pressure times area times delta x. Area times delta x, that's the change in the volume of the system, up to a possible minus sign. So the work that I do is the amount by which I change the volume times the pressure. Now I want to, well, I'll come back to that in a second. Okay. So I can say that the energy of the system changes when I change the volume. It changes because I've done work on the system. That work changed its energy. The relationship between the change in energy and the change in volume is change in energy is equal to pressure times change in volume, except what's the number one most common mistake in physics calculations? Get the minus sign wrong. So, and that's, the rest of your life, if you're going to do physics, you'll be worrying about minus signs. And they're very easy to get wrong. You should always check them. So, I have to ask myself, should I put a minus sign here or not? Okay? Well, if I change the volume decreases, delta V is negative, right? What happens to the energy? Volume decreases, what am I doing? Am I pushing in or am I pulling out? Pushing in. Volume decreases, energy increases, minus sign. If the gas itself is expanding, doing work against me, that work is coming at the expense of the energy in the gas. So its energy goes down by the amount equal to the work it did on me. Always check the minus signs. And so we can think of pressure as partial derivative of energy with respect to volume. Let's say with the number of particles fixed, or everything else fixed. Well, there's one important thing. If we're going to talk about pressure in the context of statistical physics, where we're applying our most fundamental assumption about accessible states being equally likely, then we should always imagine that the changes are slow. Push in slowly, pull out slowly. Why is that important? Because I want to be able to apply the assumption at all times. And there's always some time scale for a system to seek out its most probable configuration. We won't actually worry much about those time scales, except maybe at the very end of the course. They're short. But if we go too fast, the system might not stay in its most probable configuration during the change. If we go sufficiently slowly, and I'm not going to tell you exactly what sufficiently slowly means, but it has to be sufficiently slowly, then the system can stay in equilibrium at all times during the change. Okay? Push in slowly. At all times, we can think of it as being quasi-static, hardly changing at all. It stays in its most probable configuration. Okay? And we call such changes reversible. It means slow enough so system stays in equilibrium while changing. Well, the volume is changing, but at each moment, for that particular volume, we can think about the system being in its most probable configuration. That's reversible. How do I know it's reversible? Well, suppose I compress the gas like that. How do I reverse that? Pull it out like that, right? So if you make a slow change, you stay in the most probable configuration, and you can make a slow reverse change, which will take you back to the configuration you were in to begin with, namely the most probable configuration for that value of the volume, in this case, because we're changing the volume. Okay. Now, there are actually there are various types, more than two. There are various types of reversible change. Okay? There are two in particular that we're going to want to distinguish carefully. One is usually called adiabatic. Maybe a better name would be isentropic. But we're stuck with adiabatic, just like we're stuck with partition function. Can't fight City Hall. Use the names everybody else uses, okay? What does it mean? It means that while we're making the change, the system is not in thermal contact, it's thermally isolated. Okay? So I am changing the volume, but I'm keeping very good insulation around the box during that time. So there's only negligible heat flow between the gas and its surroundings. Okay? Adiabatic means system is thermally isolated, not in thermal contact with something. Actually, you can fight City Hall, but you can call it isentropic if you want to. What do I care? And the second type of change that we'll talk about is called isothermal. That means while the system is changing, you can imagine again it's a gas whose volume is changing, that it remains in contact with the reservoir in thermal contact. So there can be energy flow between system and reservoir during the change. So what's going to happen to the system in that case? Well, it's going to stay in equilibrium with the reservoir, okay? Which therefore means that what is unchanged while the volume is changing? The temperature. That's why we call it isothermal. So S is in thermal contact with reservoir during change. And the reservoir has temperature tau. And the reservoir is so huge that its temperature doesn't change when you take some energy out or put some energy in. The temperature of the reservoir is fixed. Hence, isothermal. So now we can think about pressure in two different ways, because we can imagine changing the volume under either one of these two conditions, for an isolated system or for a system at fixed temperature. So what I discussed initially is the case of an isolated system, because I said the change in the energy of the system is the amount of work I do on the system. Right? I'm taking it for granted that there's no flow of energy into or out of the system other than that produced by my work. That's the adiabatic case. So our observation thus far is that pressure is minus the change in energy divided by change in volume when the change is adiabatic. Okay. There's another way of describing what you mean by adiabatic. It's a partial derivative with some quantity held fixed. What's being held fixed? Well, I claim adiabatic means equivalently change with entropy held fixed. Why is that? Well, think about our definition of entropy. It comes from counting states. So you've got a bunch of energy levels of a system. If it's a big system, there are many energy levels, and they might be packed closely together. So look at the energy of a state as a function of the parameter we're changing, the volume. Well, each state maybe has its energy increasing. Like, you learned about the quantum mechanics of a particle in the box. And look at some particular state, like the ground state, you squeeze the box, the energy goes up, right? Smaller volume. And we have an initial ensemble, which we can think of as a uniform ensemble on accessible states. All the states in a certain range in energy are occupied. And then we change the volume. Well, those states don't disappear. Those energy levels vary in some smooth way as the volume changes. Okay? And so the system will evolve to a state with the same number of accessible states. Each one of the states that's accessible to begin with becomes a state which is accessible after the change. It's the same uniform distribution on the same set of states, but the way the states are distributed in energy is different. That's why the energy averaged over the ensemble can be changing, because each energy level has its energy changing. The number of states doesn't change. So states do not appear or disappear during the change. The multiplicity after the change equals to the multiplicity before. The same is true for the logs. The entropy is a constant. Kind of a hand-wavy argument. I got hands. I'm going to wave them, okay? But it's the right idea. States don't appear or disappear, and hence entropy doesn't change. when the system is isolated. So pressure really means derivative of energy with respect to volume with entropy fixed. That's adiabatic change. Change for an isolated system. Okay. Well, I'd also like to consider other types of change, like isothermal change. So to warm up to do that, let's put together the two things we've learned about the relationship between pressure, temperature, energy, volume, and entropy. And we'll put them together in an equation which is important enough to be called the thermodynamic identity. Okay. So, energy changes with entropy fixed by an amount which is minus pressure times the change in volume with entropy fixed. Okay? Change in energy for an isolated system. Well, we also know that when we change when we change the energy with the volume fixed, how does the entropy change? Its derivative is 1 over tau. So we could say the change in energy when volume is fixed is given by temperature times the change in entropy when volume is fixed. Okay? Now let's put the two things together. Suppose that entropy and volume are both changing. All right, there are these two first-order changes, so that the change in the energy when both the entropy and the volume are changing, I can write as tau d sigma, temperature times change in entropy, minus pressure times change in volume. And if you want to be traditional, we can go to the conventional units of temperature and entropy. Like I said last time, we can write temperature as Boltzmann's constant times temperature. Our temperature tau, the temperature with dimensions of energy, is Boltzmann's constant times conventional temperature. And our entropy sigma, which is dimensionless, is conventional entropy divided by Boltzmann's constant. So I can also write this as du equals TdS minus PdV. That's the thermodynamic identity. Tells us how to relate changes in energy to changes in entropy and changes in volume. Well, we've already seen what the interpretation of the second term is. It's the work done on the system, or if it's negative, the work done by the system. And what's the interpretation of this term? What else changes the energy of the system besides the work I do? Heat flow. This is the heat added. When it's positive, it increases the energy. When it's negative, that means heat flows out. System energy goes down. Now we can do some remarkable manipulations. Instead of saying du equals tau d sigma minus p dv, How about saying tau d sigma equals du? Oh, wait a minute, I better get this right. Plus PdV. That's a sign change I'm confident in. Okay. And that's another form of the thermodynamic identity. Well, we've made kind of a subtle change in viewpoint in going from one to the other. So there are these three things that are changing to first order. Energy, entropy, and volume. The changes are related. I can think of the energy in the original form of the thermodynamic identity as a function of the entropy and the volume. And then what I've written is equivalent to saying that if I take the partial derivative of energy with respect to entropy sigma with the volume fixed, that's tau, the temperature. And if I take the partial derivative of the energy of the system with respect to the volume with the entropy fixed, that's minus pressure. Okay? The other equation with the box around it is appropriate to use when I consider instead the entropy to be a function of the energy and the volume. I've inverted the function, now writing the entropy as a function of energy and volume. And this is a statement about its partial derivatives. The derivative of entropy with respect to energy with volume fixed, that means this is 0. So I divide this by this, and I get 1 over tau. And if I consider entropy to be a function of energy and volume, if I take the partial derivative of entropy with respect to volume and keep the energy fixed, so now I'm keeping the energy fixed, du is 0, and I'm dividing d sigma by dv, so I get pressure divided by temperature. So you can think about pressure that way, too. If I think of the entropy as a function of the energy in the volume, it's telling me about what happens to entropy when I change volume and keep the energy fixed. That's pressure divided by temperature. But it all comes down to this. It's real simple, right? It all comes down to this identity, which I can also write this way. This one is useful when I think of the entropy as a function of energy and volume. This one is useful when I think of the energy as a function of entropy and volume. Okay. So far we aren't necessarily saying a question. What is S? When I went from tau d sigma to TDS, what was I doing? I was, in fact, defining units of entropy and temperature differently. So remember, as I reviewed at the beginning of the class, we're defining the entropy sigma to be a quantity without units. It's the log of a pure number. And we're defining the temperature to have the units of energy. Since it's 1 over the temperature is the derivative of a pure number with respect to energy. But people usually speak of temperature in degrees Kelvin. And entropy, I don't know what the units are. Anyway, the relationship between the conventional way of expressing the units of temperature and entropy. And our way is that there's some conversion factor called Boltzmann's constant, Kb. And that means that tau d sigma and T ds are equivalent. And so I'm going to be talking about tau d sigma to remind you that tau is energy and sigma is dimensionless. But if you want to compare to some thermodynamics book, you'll see TDS. It's just a question of units. Okay. So now, I want to continue to consider an open system. How are we doing? You need a breather? You look kind of exhausted. All right. Well, take a 5-minute break. No, sorry, 5-second break. All right. 2, 3, 4. Okay, all refreshed. So now, I want to continue to consider an open system. And now let the system be large. The reservoir is even bigger. I don't care how big the system is. The reservoir is even bigger. But the system is big. So now, S is big, but there's still a reservoir, and it's much bigger. So, remember, according to Boltzmann, the probability of the system being in a state which has energy E is 1 over C times e to the minus c over tau. And we know that means that the system would prefer to be in a lower energy state than a higher energy state. Because the reservoir is stingy, big as it is, it doesn't want the system to borrow too much of its energy. On the other hand, the system really wants energy because it has more states when it has more energy, right? So the reservoir does not like to give or loan energy to S, but S wants more energy. So it can have more accessible states. Now, there's some tension. It's like the Democrats and the Republicans. They're going to have to compromise. Yeah, I wish. Okay. Remember, if you look at the system, it has a multiplicity, which is, I can write as E entropy of system divided by temperature. I hope that's not confusing. The temperature is the temperature of the reservoir. Now I'm talking about the entropy of the system. I'll call it, I'm not going to continue doing this, but I'll call it sigma sub s for system, just to remind you for now. Okay? So more entropy for the system, that's good. It has more entropy when the energy is higher. The probability distribution for a state of the system, well, I'll just write it this way, is going to go like that multiplicity, e to the sigma, divided by tau, times the Boltzmann factor, which I'm now going to write as e to the minus energy divided by tau. And I guess I'm not being very notationally consistent, since I called u the average energy before, but we know it's all going to come down to the same thing for a closed system, because we're going to wind up in the most probable configuration with small fluctuations. So if you don't mind, I'll now use energy as of the system. I'll denote it by U for a minute. And so this tension between the two things, the two desiderata, can be represented by this multiplicity factor, which is shooting up as a function of system energy, and the Boltzmann factor, which is shooting down. Okay? And the probability distribution is then proportional to the product of the two, and it's got a sharp peak. And that's where the system is going to want to be when it's in contact with the reservoir. And now we're talking about the most probable configuration for S for an open system in contact with reservoir, where the reservoir has temperature tau. So there's a probability distribution for the system energy. Let's write it again. It's an exponential of minus 1 over tau. And then energy. What the hell happened here? Why don't you guys stop me when I do stupid things? I distracted you with all that politics, I think. It was a mistake. The multiplicity is e to the entropy. And then the Boltzmann factor is e to the minus energy over tau. We should have a convention, like someone shouts, "Idiot!" when I do something like that. All right. So, u minus sigma tau. Is that right? Yeah, I guess that's not too bad. Okay. So, it's got a very sharp peak. Where is the peak? It's where the argument of the exponential is stationary as a function of energy. Sigma is a function of energy. And so, tau is fixed. That's determined by the reservoir. But the peak is going to occur at a value of u where the argument of that exponential vanishes, has a derivative which vanishes to first order, where it's stationary. So equilibrium in contact with the reservoir, the most probable configuration, is where u minus sigma tau is minimized. Because I wrote it as the exponential of minus something. We want the probability to be as high as possible, so we want this quantity in parentheses to be as low as possible. So that shows the trade-off, right? Low energy helps us to minimize this. High entropy helps us to minimize it. The entropy is a function of the energy, and so we're going to find a preferred value of u hat, determined by d du of that quantity, u minus sigma tau, equals 0, or 1 minus d sigma du times tau equals 0. Well, it's just the same. Well, you see, I just said so if you forgot to shout idiot. It's just the same old story, right? D sigma, d tau. Did it again. Boy, I'm having a bad day. 1 over tau. The interpretation is a little different now. That's going to determine u hat. That is the optimal compromise between the two desiderata. The system having low energy to make the reservoir happy, high entropy to have as many states as it can. Now, it's useful to write this peak probability up to some prefactor, which we won't have to keep track of. We're really writing its logarithm, but I'll write it. I'll say this is approximately e to the minus some function of temperature divided by temperature. And this is the value of this expression, u minus sigma tau, where it's stationary. Okay? So by f of tau, a function of temperature, I mean u minus sigma tau. That's the quantity in the exponential here after I take out the minus 1 over tau. But evaluated where it's stationary with respect to u. So here, sigma is a function of energy. And we've done some kind of transformation to get a function of temperature. And we've done that by evaluating this expression involving the energy and the temperature, where it's stationary with respect to u. Then we eliminate u, because we fixed u to be that particular value, and we obtain some function of temperature. Where that minimum occurs, and the value of this expression, where it occurs, that depends on temperature. Now, this transformation, where we traded in a function of energy to get a function of temperature, is an example of what's called a Legendre transform. Well, that doesn't actually matter, but just so you know, you can look up Legendre transform in Wikipedia if you've got nothing better to do. But this is what it is. And this function of temperature has a name. It's called the Helmholtz free energy. Because in thermodynamics, we try to be careful to, name things after people. Usually it's the wrong person, but anyway, it all evens out in the end. Everybody gets something named after him or her. So what's the big deal? Why do we care about Helmholtz free energy? A couple of reasons. Well, why do we care about it? Assuming, do we care about it? I think we do. Well, here's one reason, which is going to be very useful in the next lecture. So when we evaluate the partition function, well, in general, whether the system is large or not, that's some function of temperature given by the sum over Boltzmann factors for all system states. Okay? The temperature determined by the reservoir. Now, the system is large. That sum is going to be dominated by the most probable configuration and small deviations around it. So I can write the partition function, and this is true for a large system, as e to the minus free energy divided by tau. Okay? And in other words, the free energy is going to be minus tau times natural log of partition function. So that's good because it'll be easy to calculate the free energy for a large system. If we can do the sum to evaluate the partition function, all we got to do is take its log and multiply by minus tau. That doesn't explain why we care about Helmholtz free energy yet. Well, we care about it because we'd like to consider making slow changes when we, say, vary the temperature. Okay? What if the reservoir's temperature is going to change? So far, we've just saying it's really big and it's fixed. But if you're doing an experiment in the lab, say, you might adjust a thermostat so your system comes to equilibrium with the reservoir at a new temperature, and you want to know how the system is going to behave when the temperature changes. So F is useful when we consider reversible changes in temperature and volume. So, where did I write down what F is? Here it is. So, F is equal to U minus sigma tau, but it's U minus sigma tau at a particular value of U, right? It's the value where this is stationary. So if we change the temperature a little bit, then the most probable configuration is going to change a little bit, right? The U hat, where it's stationary, is going to change a little bit. How does the free energy change? Well, the F, that's the first order change in U minus tau sigma. And I think no one would disagree if I said if tau, sigma, and U are all changing, I can write that as du minus tau d sigma minus sigma d tau. Okay, because I just differentiated the second term with respect to the product rule, using the product rule. Now, if we stay in the most probable configuration, this is equal to 0 in equilibrium. And so the change in the free energy when I change the temperature a little bit and I stay in the most probable configuration is a minus sigma d tau. So here I'm considering keeping the volume fixed, I should have said. So I'm keeping the volume fixed. I'm adjusting the temperature. So the conclusion is that if we make a change with the volume fixed, the change in the free energy is going to be minus sigma d tau with volume fixed. Okay? Well, what does the thermodynamic identity tell me when I consider changing the volume as well? Since it says du is equal to tau d sigma minus p dv, that's the thermodynamic identity. But at a fixed temperature, U is determined by the condition that du is equal to tau d sigma when I evaluate the Helmholtz free energy, right? Now, the Helmholtz free energy, its change, when I keep the temperature fixed, is just du minus tau d sigma. Maybe I should say it that way. So with temperature fixed, dF with temperature fixed is equal to du minus tau d sigma, and the thermodynamic identity says that's equal to minus p dV with temperature fixed. So I can write a new version of the thermodynamic identity which is appropriate for a situation in which I'm changing the temperature of the reservoir and the volume of the system. If I'm changing both the temperature and the volume, I can write dF equals minus sigma d tau. That's this. When the volume is fixed, that's how it changes. When the temperature is fixed, this is how it changes. So minus p dV when both the temperature and the volume are changing. I guess I'll put a box around that one too. So now I'm inviting you to think of the free energy. Well, we've seen how it became a function of temperature. We eliminated the energy by evaluating this quantity in the most probable configuration. Of course, the energy of the system also depends on the volume. So although I hadn't indicated it explicitly here, it was implicitly a function of temperature and volume. So now you can think of the free energy as a function of temperature and volume. And this equation is just telling you what its first partial derivatives are. Derivative, just to restate what I've already said, the partial derivative of Helmholtz free energy with respect to temperature with volume fixed is minus entropy. Partial derivative of Helmholtz free energy with respect to volume with the temperature fixed is minus pressure. And the reason this is a useful thing is that when I consider keeping the system in contact with the reservoir while I change it, and I change the temperature of the reservoir, this tells me how to do the accounting to keep track of work done by the system, right? Because when the temperature of the reservoir changes, that will induce some heat flow from system to reservoir or from reservoir to system, depending on whether I'm heating up, increasing the temperature of the reservoir or decreasing it. And that means some energy flow into and out of the system will not be ours to use. It will be bound, it's sometimes called. Not something that we can apply or exploit. It's necessary just to stay in temperature equilibrium with the reservoir. But if we keep the system in contact with a reservoir which has temperature fixed, again, there's going to be some heat flow, because if I compress the system, if it's going to stay at the same temperature, there's going to be some energy flow out of the system. And that we can't use to do work. But when the temperature is fixed, the work that gets done by the system or gets done on the system when its volume changes, that's what the Helmholtz free energy is keeping track of. Okay? So, Helmholtz free energy is useful if, for the second situation I described, where we have a system of variable volume in contact with the reservoir, when volume of S changes, and temperature of R stays fixed, there's going to be some heat flow either into or out of the system. The usable work that we can extract from the system or put into the system while the temperature is fixed, that's what Helmholtz free energy keeps track of. With the temperature fixed, dEF is equal to minus P dV. So dF is work done on, or by, if it's negative, isothermally. And coming back to this observation, well, we have a nice way of computing it if we can figure out how to sum over states to get the partition function. We can evaluate the partition function. We take its log. We multiply by minus tau. And then if I want to know what entropy of the system is, or pressure of the system, I take that function, f of tau and v, and differentiate it with respect to tau to find entropy, or with respect to v to find pressure, which is actually what we'll do next time when we talk about an ideal gas. Well, there's some trivial, but nevertheless, well, it's not fair. You should never say trivial. That's bad teaching. Nothing's trivial. There are some easy-to-derive well, that's not good either. There are some consequences I will now derive in a brief derivation of this statement about the partial derivatives of the free energy. Actually, I'm going to derive one consequence. There are many others which can be derived using a similar argument. So this is an example of what's called a Maxwell relation. There are many Maxwell relations, and this is one of them. Many relations, but it's all the same Maxwell. We name everything after somebody. And the observation is partial derivatives commute. So in other words, if I have a function of tau and v, I can take the partial derivative of v with tau fixed after taking the partial derivative with respect to tau with v fixed of f, and I'd get the same thing if I differentiated in the other order. If I took the partial derivative with respect to tau with v fixed after taking the partial derivative with respect to v with tau fixed, it's the same thing. That's what I mean by partial derivatives commute. Order doesn't matter. And that means that since the partial derivative of free energy with respect to tau with v fixed is also known as minus sigma, minus partial derivative of sigma with respect to v with a tau fixed, since that's what this is equal to, partial derivative of free energy with respect to volume is minus pressure. So that's equal to minus derivative of pressure with respect to temperature at constant volume. And we can get rid of the minus signs because there's one on each side. And that's one of the Maxwell relations. They're all derived by the same idea, using partial derivatives commute. And in fact, it's a not so obvious property if we consider how entropy changes when we change volume isothermally. It's related, in fact, equal to how pressure changes when we change temperature with volume fixed. Okay. Boy, talking too fast. A lot of pages today. Am I talking too fast? No? Too slow? Question. Could you repeat it? Sorry. Okay. Okay. So the mathematical observation is that partial derivatives commute. Does that? You want me to explain that? Okay. So then the consequence of that is we've seen that if we think of the free energy as a function of temperature and volume, the derivative of free energy with respect to temperature with volume fixed is minus the entropy. So except for a minus sign, this is the same thing as differentiating entropy with respect to volume. On the other side, when I differentiate free energy with respect to volume, that's minus the pressure. So this expression, aside from the minus sign, is the derivative with respect to temperature of the pressure, in this case with volume fixed. That's the Maxwell relation. Okay. Yeah?
I have a question. When you were taking derivatives there, you assumed that temperature wasn't a function of energy?
When I was taking the derivative here, the context was I'm considering a system in contact with a reservoir.
Oh.
Reservoir is very large. Its temperature is fixed. The temperature doesn't change when the reservoir gains or loses energy. Therefore, yes, tau was a constant. And then I was trying to figure out how much energy is the system going to want to borrow in order to find the overall most probable configuration, taking into account how borrowing energy from the reservoir would decrease, if the amount of energy borrowed was positive, the number of accessible states of the reservoir, but it would increase the number of accessible states of the system. And the most probable configuration is the optimal way of getting the product of the number of system states and the number of reservoir states as large as possible. Yes?
I have a question about the final result for maximizing or minimizing that. Isn't that the definition you gave for temperature?
Yeah, but now the interpretation is a little bit different because I originally gave the definition for a closed system, right? And I said, okay, for a closed system, the number of accessible states is a function of the energy. Its logarithm is a function of the energy. That's sigma of u. And I'll define temperature as d sigma du equals 1 over tau. So now I'm saying something a little bit different. On the other hand, it's an obvious consequence. I'm saying that if the system is in contact with the reservoir, then the energy of the system is going to adjust so that d sigma du of the system is equal to 1 over the temperature of the reservoir. It's not the definition, but it's an immediate consequence of the observation that the system will come to temperature equilibrium with the reservoir. Actually, I'm glad you pointed it out, because I should have said so at the time. The result doesn't surprise us. It's just the statement that in the most probable configuration, the system's temperature matches the reservoir's temperature. Okay. Well, okay, I got 5 minutes. And actually, are there more questions? I'll just give a preview of what I want to do on Thursday. So what we'd like to discuss next, we're the first couple of weeks of this class, we're revisiting concepts that you've seen before, but from a somewhat different point of view, I hope, like temperature and entropy, energy and free energy. And the next lecture is actually not the first. No, maybe it is not the last that you're going to hear about a system you're familiar with, the ideal gas. And so, actually, we're going to be revisiting the ideal gas a number of times, each time with a new physical wrinkle added. But the first thing we're going to try to understand is the good old classical ideal gas that you learned in classical physics in high school. And then we're going to see that there can be rather profound changes in the behavior of an ideal gas in what we call the quantum regime, where there are really two different types of gases, Fermi gases and Bose gases, depending on whether the particles are fermions or bosons. But the first step is just to understand the classical ideal gas. But in keeping with the philosophy of the course, we'll start by looking at that from a quantum mechanical point of view. So it's handy that you took Physics 12b last term because you learned about a particle in a box, right? And so you know that if you have a particle in a three-dimensional box, and let's say it's a cubic box with side L, what the energy eigenstates are for a particle in a box. You can write the Hamiltonian as a minus h bar squared over 2m times gradient squared for a free particle. Because that's just the kinetic energy of a particle, p squared over 2m, right? Stop me if you haven't heard this before. And therefore, we can write the energy as a function of three integers. Where the integers count the number of nodes of the wave function in the x, y, and z directions. Well, this really depends on boundary conditions, and for our application, it doesn't really matter what boundary conditions we choose. But let's suppose I use the boundary conditions where the wave function psi, as a function of x, y, and z, vanishes at the walls of the box. And we can put the walls at x. X can be, well, it's L by L by L. This is the origin. And the walls are displaced by distance L in the x, y, and z directions from the origin. The energy eigenstates just factorize up to some normalization constant. They can be written as the sine of m times an integer, which I'll call nx, times x divided by L, and a sign for the dependence on y, and a sign for the dependence on z. So there are three integers, and they can't all be 0, or else the wave function would be 0. They're all required to be integers to be consistent with the boundary conditions. And they are all eigenstates of this Hamiltonian. The gradient squared can be written as the sum of gradients squared for x, y, and z. So all that should sound familiar, right? Okay. And so the energy can be written as h bar squared over 2m pi over L squared the sum of nx squared plus ny squared plus nz squared. So now we can ask ourselves, suppose you got a single particle in the box. Can we evaluate its partition function? And we can. And it's especially easy to do so in a certain limit. We want to find z, the sum over states, e to the minus energy of state over tau. Now the sum over states means summing over the integers nx, ny, and nc, in the case where they're not all 0. And we want to do this sum. And it's easy in the case of, well, I'll call it low density. It's actually just one particle in the box so far. But low density means a sufficiently large box. When the box is sufficiently large, then we can approximate that sum quite well by an integral. And it's always the greatest thing. It makes your day when it turns out that the integral you have to do is a Gaussian integral because it's the one we know how to do. And so in the case of a large box, evaluating the partition function becomes a good old Gaussian integral. We can evaluate it. And then we want to make a big step. We want to go from the case of a single particle in the box to the case of many particles in the box. And we want to continue to be able to count the states and sum up the contributions from all the states to get the partition function. And we'll talk about that on Thursday.